And we're recording today. It's a Saturday. We're doing our Saturday school review at Talon. So for those of you who couldn't make it, that's why I'm going to post this for all of you on YouTube. I decided that probably the best thing to do before we take our test is to make sure that you guys are very solid on your understanding of the concepts of active and passive transport. Your test next week, Tuesday, right? Tuesday, is going to cover cells and homeostasis. So don't forget, you've got to go back and review your organelles in chapter 4. Okay? So we need today to talk about equilibrium and what that means, and look at the differences between diffusion and osmosis. Don't forget, you're supposed to be filling in a word wall as we go through this. It was the page opposite your table of not table of contents, your title page, and you should have words on your word wall. Diffusion and osmosis, I would expect, are there. Now, I know this is something that you guys covered in the 7th grade. Okay? But looking at our quiz grades so far, we're still having a problem understanding what these concepts mean. We're going to look at how substances can move across cell membranes through facilitated diffusion, and how ion channels help assist moving things. So first of all, diffusion. Diffusion is a passive transport process, and anytime, all of these that we're going to talk about in this first half of the lecture are all passive transport, which means what? There's no energy required. No energy required. And so we are always looking at movement from a high concentration to a low concentration. And the analogies that I like to think about is if you're at a playground and you're on a slide, right? You climb up the ladder to get on the slide, right? There you are. And then you slide down the slide, and it doesn't require any energy on your part, right? You just go down the slide. Whereas if you wanted to actually climb back up the slide, it would take energy, and that would be like going from a low concentration to a high concentration. The other example I use in class is you're packing a suitcase. And your suitcase is already really, really full. But you keep trying to put things in the suitcase. Is that high to low concentration or low to high? That's low to high if you're trying to keep packing that suitcase. Whereas on its own, stuff's going to fall out of the suitcase where it's really crowded. So that out of the suitcase would be high to low. Packing it fuller and more full, that's going to be low to high. So, diffusion is a type of passive transport, specific type of passive transport area from high concentration to low concentration. They talk about driven by the molecule's kinetic energy. Remember, we looked at something called Brownian movement. That there is natural vibrational energy that molecules have. They're always moving. They're never completely still. And so because of that vibrational energy, they're going to be bouncing into each other. If they're in an area where they're tightly packed in a high concentration, then as they bounce into each other, they're going to ricochet off in all kinds of different directions. Now, in the air around us, are there molecules? Yes. Oxygen, nitrogen, carbon dioxide, carbon monoxide. All these different oxygen. If someone had farted, there's methane there too, right? All of these particles are going to be bouncing into each other and into other things. And so that's why particles want to go from an area of higher concentration to an area of lower concentration. And I'm trying to go to the next slide, and I'm having an issue here. Okay, page down, and we're not. There we go. So, why is the term passive transport appropriate? If you're passive about something, what, Chris?
It means that you're okay with it easily, like passive cell or like a molecule can pass through easily.
Okay, so passive, you're saying it happens easily. It passes through easily. Okay, Sinclair, what do you want to say? Not putting out any energy. So if I said, don't be a passive learner would be somebody that would just sit there, not take any notes, not put in any energy into understanding a concept. Whereas an active learner is going to be somebody who's going to be doing things, putting energy in. So passive transport is just going to happen on its own because of the molecule movements. So here I had some videos. I've checked these links. They're great videos to watch. You shouldn't just watch them once. I would watch them again for the Khan Academy explanation and explanations of Brownian movement. Okay. Sometimes we have diffusion across semi-permeable membranes. The cell membrane is semi-permeable. Another word for that is selectively permeable. That means certain things can pass through and others cannot. There's sometimes openings in the membrane itself that allows for things to pass through. So why do molecules want to move? They're because of random movement, and they want to collide as least as possible. So they want to spread out as much as they can. So here is a diagram showing the diffusion of this lump of sugar in a liquid. Okay, but we also have diffusion of molecules, one gaseous molecule into another gaseous molecule. So check those out. Osmosis now. Osmosis is a type of diffusion. Okay, osmosis is a type of diffusion. So we are still going from an area of high concentration to an area of low concentration. But now we're specifically talking about water and a cell membrane. So what makes osmosis different from simple diffusion is that we're talking specifically about water molecules moving, and we have now a selectively permeable membrane. Remember, our membrane here is a lipid bilayer. You have a phospholipid head with tails. And the heads like to be in contact with water, but the tails do not. So we call that hydrophilic is loving. Okay. Philos means love. And then the center is hydrophobic. If you have a phobia of something, you have a fear of it, right? You know that word. So water molecules are going to be able to move freely across that membrane. And so what is the phrase that we use to remember how to tell where water molecules are going to move? Where salt is, water follows. So you have to look very carefully when you see a diagram, what is being identified as the salt molecule, what's being identified as the water molecule. And remember, salts aren't just sodium chloride. It's going to be anything that's dissolved in solution. Okay, so the net direction of osmosis. What do we mean by net direction? Okay, we're talking about the gain, the overall gain. And so this is why when I drew my little cell, I said I'm going to use a big arrow to represent the net direction of water and a little arrow to represent that, yes, there's still water going in, but in this case, what would happen to this cell if the net movement of water was out of the cell? Okay, it will shrivel. Okay, but water is still always moving in. But if more water moves out than moves in, then your net movement is out. What would make water move out of this cell? More salt. If you have more salt, if you have an elevated salt level outside this cell, water is going to move out. What kind of solution would that make? Hypertonic. If the salt concentrations were equal inside and outside the cell, then it would be isotonic. And if the net movement of water was into the cell with a little bit of movement of water out, that's hypotonic. What would happen to the cell if the net movement of water? It could potentially burst, and that's hypotonic. So I told you the story about my fish. True story, you guys. Horrible story. Okay, here's the story about my fish. My fish at home. My fish, Mary Kate. Mary Kate had very dirty water in her bowl. This is true. And I wanted to clean her bowl. And so I thought, well, I don't want to just use regular tap water because there's chlorine in that. So I went over and I pulled water out of my drinking water spigot that comes at my sink. It's purely a really nice clean water. It goes through a really a really extensive purification system, right? It's pure drinking water. And I thought, well, then there won't be bad stuff in there. I just wasn't thinking. I just thought it would be good water for the fish. And so I dumped the Mary Kate's water out. I filled it up with this really nice water solution. And after a few minutes, Mary Kate started swimming kind of in circles and on her side and then wouldn't move for a little while. And the fish was acting really weird. And I was like, my mom was there, my kids were there. They're like, something's wrong with the fish. And I said, I don't know. I just changed the water and she's acting all weird. And the water was the same temperature as it was before. And the fish was in shock. And my daughter says, Mom, what kind of water did you use? And I said, well, I used the purified drinking water. And I went, oh my God. I put that poor fish into a hypotonic solution. The water that I used for the fish was so pure that it actually had a lower salt concentration than the fish's cells. So here's the poor fish's cells, and maybe that cell is, 90% water, 10% salt, but I put it into a solution that was probably 95% water. It was really pure. So water was flooding in, causing massive cell damage, which was affecting the fish's equilibrium, and it was killing the fish. I was watching it die. It was horrible. I went, oh my gosh. I just went and got regular old tap water, because that's what I usually always use, right? Regular old tap water, because I figured that would be more isotonic to the fish. Scooped her out, changed the water in the bowl, plunked her back in, and then we waited. And she acted weird for a little while, and then she started kind of swimming straight. And I thought for sure the next morning I was going to have a floater, but she's fine, and she's still alive. And Rachel, is that not a true story? It's absolutely a true story of how I almost killed the fish because I forgot about osmosis. And it was not a Harambe event, okay? It was Mary Kate, my goldfish. So, be careful with your fish. Don't use distilled water on your fish.
I always feed it too much and then they end up dying.
You always heated it too much?
No,
feed them too much. Oh, well, that's another problem, right? Okay. Just don't have fish. I like fish. Okay, so we talked about hypertonic. Hyper means more, right? More solute than the cell. And so water will diffuse or leave the cell. That wasn't what was happening, though, right? My fish was poor in, not in an isotonic solution. No net movement of water. Does that mean water isn't moving at all? No, it means that the water is going in and out equally, and you're not having a net change in the water. Okay, where salt is, water follows. My poor fish. Very salty solution. Now, if I put my poor fish into the very, very salty solution, what would have happened to it? It would have become like the sailor in the sea, right? Drinking too much drinking that salt water and dehydrating itself. So, hopefully you guys will remember my poor fish. All right, so how do we establish equilibrium when diffusion happens? What's the difference between diffusion and osmosis? How does facilitated diffusion work? And how do ion channels work for diffusion? So here we have our 3 blood cells. This was a diagram that you drew in your interactive notebooks, right? And you need to, whether this is a red blood cell or any cell in our body or my poor goldfish cells, same idea. Please look back at this diagram, and it's in your textbook. And this exact same diagram, you drew this on the left-hand page of your notebook, and make sure that you have a good explanation, because you can expect to see questions about hypertonic, hypotonic, and isotonic on your test next week. So how do cells deal with osmosis? Cells have to compensate. And if you're a single-celled organism, if you're only 1 cell big, you compensate in a different way than if you're an organism that has an excretory system. We have kidneys, and our kidneys help us to compensate with that. So for an organism like a paramecium, they have a structure called a contractile vacuole. Okay, and I have a nice little YouTube video for you to watch and look at the contractile vacuole. Basically, what happens with the contractile vacuole is, here's the paramecium cell. It looks kind of like, you'll see the structure fill up, and then all of a sudden it squeezes and it's gone. And what happens is as that vacuole, and you remember what a vacuole is, right? As that vacuole fills up with fluid, with water, then it will contract, and when it gets to a certain volume, contract and expel the water out of the cell. So if the paramecium is put into a hypotonic solution, and so water is flooding into the paramecium, it has a way to get rid of that excess water so that it doesn't burst. We don't need contractile vacuoles, because how do we get rid of excess water? We would urinate more. So our kidneys would work to help us get rid of the extra water. So make sure you watch, please, the YouTube on the contractile vacuoles and the paramecium. Facilitated diffusion. Okay. If you're not familiar with the word to facilitate, it means to help or to assist. So this is going to be diffusion that is assisted or helped by a molecule that is embedded or are on the surface of the cell membrane. Okay? And so because of the assistance of this carrier protein, it facilitates the movement of molecules across, but it doesn't require energy to do that, because we're still going from high concentration to low concentration. And here's the key: it's still going down the concentration gradient. It's just using a membrane protein to help move down the concentration gradient. We're going to learn about the other kind of active transport where you need a protein in the membrane, but it's pushing against the concentration gradient. So whenever you hear high to low, concentration, you know it's going to be a passive transport. If it's high to low concentration and you're using a membrane protein, then you have facilitated diffusion. So, why is facilitated diffusion necessary? Why do we sometimes have to use a membrane protein? Why doesn't everything just go straight through the membrane? Yeah. Exactly. Sometimes the molecules are too large, and so it would rip a hole in the membrane if it just went straight through. So we have to use a protein channel to pass through. Good. And so here we have facilitated diffusion. Okay. Here we have another diagram, and I don't think you guys drew this in your interactive notebook. Did you have to draw this? No. Okay, but please, this diagram is in your textbook. Take a look at it. Read what it says, that we have a molecule that binds to the outside, and it changes the shape of the carrier protein, which allows the molecule to move from the outside of the cell to the inside of the cell. But it does not require energy. We also have ion channels. These are groups of proteins or singular proteins that allow things, ions, which is an atom with a charge. That's what an ion is. So a sodium atom, a chlorine atom. These will move across without energy because they're still going from high to low concentration. Okay? High to low concentration. So why are these passive transport? Because you're following the concentration gradient. Okay? Now, active transport. You need to know the difference between active and passive. Okay? Active requires energy. Passive does not. Going to look in detail how the sodium-potassium pump operates. Now, you're like, but wait a minute. Sodium and potassium, these are ions. You're right. But this becomes active transport. Why? Because you're going against the concentration gradient. You're moving those atoms or those ions around against. Then endocytosis and exocytosis, hopefully you'll think those are easy. Okay, so we can answer this question very easily, how our active transport process is different than passive. Okay, we got two reasons. One, they require energy. Okay, and two, they go from low to high. Low concentration to high concentration. So please remember, this is you're climbing up the slide on the playground. You're packing that suitcase, and you just got to get that extra pair of shoes into the suitcase, even though the suitcase can't hold anymore. Is it easy to overfill a suitcase? No. Right? That's when you have to sit on it to get it to zip up. Ever have that happen? Well, you're applying a lot of energy. You'll work up a good sweat. You're using energy to get it to close. Okay? So, low concentration to higher concentration. And it requires cells to expend energy. When we talk about expending energy, we're talking about a molecule called ATP. So we can take just a second to talk back about our organelles. Inside of the cell, which organelle is responsible for energy? The mitochondria. And a mitochondria is that double-layered organelle. And the mitochondria has a nickname. We call it the powerhouse. Oops, I misspelled that. Not the Bower House, the powerhouse. It's a great thing about these YouTube videos. It catches my mistakes forever. The powerhouse of the cell. So what does the mitochondria break down? It doesn't break down ATP. It actually creates ATP through breaking down what? No. Glucose. Don't you remember when we did our organic molecules and we talked about what is the function of sugars? You almost forgot about it. Well, you can't, because your final exam at the end of the semester is the whole semester. It's cumulative. Oh, yes. You must remember these things because these concepts are building on top of each other. Okay? Our concepts are building, so you can't forget one. There's a reason why we learned about glucose first. Because then we're going to talk about where glucose gets broken down. And then we're going to talk about how it gets broken down. That's cellular respiration. So, the powerhouse of the cell, the mitochondrion, takes in glucose molecules. And remember, C6H12O6, a very large molecule with lots of chemical bonds. It breaks the chemical bonds between the carbons, hydrogens, and oxygens, and it makes these molecules called ATP. Then the ATP moves out into the cell, and it is the ATP that becomes like a rechargeable battery. Wherever the cell needs to do work, it will pull apart ATP, get the energy needed to do the work, and then the building blocks for ATP go back and they get recycled in the mitochondria. Okay, so just like you can plug in a rechargeable battery or the battery in your phone, You use your phone, your battery life goes down, then you plug your phone back in, charge it back up. Back and forth, back and forth. We need to look back. What is the structure of the cell membrane? Okay, remember our cell membrane structure. We have all of those phospholipid heads. And then we have proteins. We call them transmembrane proteins. And don't hate on my pictures, please, because you know it's super hard to draw on these little iPads. So you can recognize that as phospholipids, right? You're laughing. You do not make rude comments about my pictures.
I apologize.
Just make sure you don't make. Watch. I'll start getting like, wow, great teacher, but you can't draw at all. Okay, so here's a little section of our cell membrane. And so sometimes you have proteins that are called transmembrane proteins because material can go all the way through. And then other times you have proteins and you can have glycolipids, sugar molecules that go out on the surface that act as identification molecules for a cell. Okay, look at that beautiful picture. Now I'm just going to erase it. So sad. So the sodium-potassium pump, okay? Oh, the key here. You're going to move 3 sodium ions for every 2 potassium ions, okay? So sodium goes, so you get 3 sodiums out and 2 potassiums in. So you get 3 positive charges moving out, but only 2 positive charges moving in. Does that look equal to you? No, it's not. Where are you going to have a net charge build up? These 2 are going to cancel out, right? And so what kind of a charge are you going to get? Here. A net positive charge on the outside of the membrane. Okay? And so there's always a difference in charge between inside the membrane and outside the membrane. Which way would ions move passively? Sorry. Text message, just rude. Oh, it's my phone? Oh, no, I knew it was my phone. I can't get angry at you guys now, huh? Because my phone went off. But it's a Saturday, so. All right. Which way would atoms want to move on their own, passively? They want to go from which direction? High to low. So which way would they want to move? Passively. Well, I put all my X's there. Maybe if I take my X's away. There's your membrane. Which way would they want to move through passive transport? In, right? If you always have more positive charge outside than inside, a natural movement would be going in. But that's not what happens. This is an active transport process. Okay? So, all right, so the sodium-potassium pump is going to be moving 3 sodiums into the cell and 2 potassiums. 3 sodiums move out of the cell, 2 potassiums move back in. It takes ATP to drive this. So describe the change in charge that is created by the movement of sodium and potassium. Did we just do that? Do you have that drawn in your notes? Did you draw something like that in your notes? Draw a little line to represent the cell membrane. It says here, 3 sodium ions move into the cell's external environment. So 3 sodiums, 3 pluses for every 2 that move into the cell. So there is an overall positive charge created outside of the nucleus and an overall more negative charge or less positive charge inside the cell. I said nucleus, didn't I? I meant cell. Okay? And so this diagram is in your textbook. ATP here is necessary to open up the sodium-potassium pump, the protein. ATP opens the channel and moves the sodium from the inside of the cell and expels it outside. Do you see how ATP turns into something called ADP plus a phosphate? So the energy is used up. This is like when you've been on your phone a lot and you've depleted the phone charge. That ADP and phosphate then goes back to the mitochondria where it can be recycled and turned back into ATP. Notice this protein can then also transfer two potassiums back into the cell. So the potassiums come back in and enter into the cell. Watch the videos. Okay, watch the video. Why would a cell need to do this? Cells will do this when they need to create a charge for an action potential. Nerve cells do this all the time. Muscle cells do this, okay? Because if you create a difference in concentrations of ions, then you can use it to your advantage as a cell to then allow things to go back by passive transport, okay? And it's a way of the cell doing work. If you're a nerve cell, you'll conduct an impulse down along your cell membrane, and then you'll release chemicals that will then stimulate the next nerve cell. Endocytosis and exocytosis. I think these are very easy, but of course I've learned them many times. But endocytosis sounds like something is going to be going in. And exocytosis sounds like something's going to be exiting, yes. So, endocytosis, this is like the cell does Pac-Man. It's going to extend its cytoplasm and envelop or ingest a particle and put it into a vesicle. Okay, we have two types of endocytosis, pinocytosis and phagocytosis. The way I like to remember this, Pinot is a type of a wine. Pinot Grigio, Pinot Gris. So, you drink a Pinot. Pinot means drinking, okay? Phagocytosis, a phagocyte is a cell, an eating cell, a cell eater. So, phagocytosis means cell eating. So, you're going to be ingesting solid particles of things. And it starts out really simply. If you have your particles here that you want to ingest, whether they're solid or liquid, your cell comes along, and then your cell will extend itself to surround those particles. And then you end up with those particles inside the cell wrapped in its membrane. And that now is a vesicle. Why do you need endocytosis and exocytosis? Okay, so to move, but why can't you just use facilitated diffusion or active transport? Why would you need this process of literally, wrapping the membrane around something? Not faster. Actually, it would be much slower, and it would take the cell a lot more energy.
Bigger things?
What?
Bigger things? Bigger
things, exactly. These are going to be things that might be whole proteins, or maybe a bacterial cell. That if this is a macrophage, a white blood cell, and its job is to eat other cells, it can't diffuse it across its membrane. It's got to surround its cytoplasm and ingest it that way. So it's going to be for even bigger things. And the reverse of this process would be the exocytosis, where the material would be going from a vesicle out and fusing with the cytoplasm and then being sent out of the cell. Okay? So endocytosis and exocytosis. Much better drawings than I just made, right? All right, so let's take our quiz. During diffusion, molecules tend to move in what direction? They never move. It doesn't depend on the concentration gradient. From an area of low concentration to an area of high concentration, or from an area of high concentration to an area of low concentration. Okay, you got to go back. High concentration to low concentration. We're talking about diffusion. And this is where a lot of you made that silly mistake on your quiz. So, two things. Don't go too fast. And don't just read the first answer. Or when you get to an answer that you think is correct, don't stop there. Read all the options. So some of you might have gotten to answer C and went, oh, low to high. Yeah, that was it. Without going on and reading high to low. So it was answer D. Ion channels aid in the movement of which substance? Ions across the cell membrane, but we aren't going to stop there. We're going to read all of them, right? Water across the cell membrane. What's it called when we're moving water across the cell membrane? Osmosis. So we're going to, that doesn't sound right. Molecules up a concentration gradient. Carrier proteins within the lipid bilayer. Ion channels aid in the movement of carrier proteins. No, but we have carrier proteins in the lipid bilayer. Molecules up a concentration gradient, but then why are they calling it a molecule channel, not an ion channel? So I agree, your answer's A, or F, the very first answer does appear to be correct. Whew. But we would want to reason our way through. If there are any answers that you can eliminate, then that reduces the number of choices if you're not quite sure. The sodium-potassium pump transports which of the following? This is when drawing a picture of it will really help you to remember. Because hopefully you can visualize 3 sodiums going out, but only 2 potassiums coming in. So sodium-potassium pump transports both the sodium and potassium into the cell, sodium-potassium out of the cell, sodium in and potassium out, or sodium out and potassium in. Sodium's going out, potassium's going in. Okay. Which process do some animals use to engulf, digest, and destroy invading bacteria? Exocytosis, penocytosis, phagocytosis, or all of the above? Phagocytosis. Now, on all of the above type questions, here's a hint. If 2 of the answers are correct, and the third one you're not sure of, but your fourth option is all of the above, if there are 2 that you absolutely know are correct, you have to choose all of the above, even though you're not sure about the other one. Okay? So if it had said endocytosis, cell eating, phagocytosis, and all of the above, then you have to choose endocytosis. I'm sorry, all of the above. Because endocytosis is correct. It's not incorrect. All right, the graph below shows the rate of glucose transport across a cell membrane versus the concentration gradient. Use the graph that follows to answer the question. And so we have the rate of transport of glucose is dependent upon the concentration of glucose. So that would be the more glucose you have in solution. What's the trend that we're seeing? The more glucose you have in solution, the more the rate increases, right? One increases faster than the other one, though. Which line represents the diffusion of glucose through a lipid bilayer? That's a hard one, huh? What's the difference between these 2 lines, X and Y? One of them's increasing faster than the other. because it's going to take a little while for stuff to go across a lipid bilayer. It's going to be a little bit slower of a rate than line X. Okay? So the rate is slower and steady. Okay? Passive transport is to osmosis as active. Now, this might be a type of question that you're not familiar with. Okay? These are called word analogies. So what you have to do is you have to figure out the relationship. Have you guys ever done these before? Yeah, you have to figure out the relationship between these two terms. And then you look for the same kind of relationship between this term and one of these. So passive transport is to osmosis. So osmosis is a type of passive transport, right? So now we're going to look for something that is a type of active transport. And I'm thinking it's endocytosis too. Let's see. Did we get it right? There's noise in the hallway. There we go. Endocytosis. Okay. This diagram here. What form of cellular transport is being illustrated in the diagram? What are we seeing? We see a vesicle inside the cell coming and merging with the cell membrane and releasing materials out of the cell. Okay, it's exocytosis, right? Good. Okay, here's a short answer question. When a cell takes in substances through endocytosis, the outside of the cell membrane becomes the inside of the vesicle. What might this suggest about the structure of the cell membrane? Think about the structure of the cell membrane, what you remember. Can you tell the difference between the inside and the outside? It's a bilayer, it's a lipid bilayer, and so it can be, yep, it can be reversed. Very good. Very good. So of course, on any of those questions, if you wanted to, if you needed more time to think, you could pause when you go back through these. This one. Some cells have carrier proteins that transport sugar molecules and hydrogen ions into the cytosol at the same time. These proteins move sugar up their concentration as hydrogen ions move down their gradient. How would the transport of sugar into these cells affect the pH of the cell's internal environment? And what would happen to the transport of sugar if hydrogen ions were removed from the external environment? Wow, there's a lot in this question, isn't there? Okay, so we've got carrier proteins that transport sugar molecules and hydrogen ions. What's the connection between hydrogen ions and pH? We looked at pH in here, yeah. Not the more basic, an increase in hydrogen ion concentration makes your pH go down, makes it more acidic. Okay? So you have more hydrogen ions. The more hydrogen ions you have in solution, the more acidic a solution is. So we need to get sugar into the cell. Okay, sugar's going up the concentration gradient, and hydrogen ions are moving down their concentration gradient. How would the transport of sugar into these cells affect the pH? So every time you're moving sugar in, you're moving hydrogen ions out of the cell. Right? I'm sorry, hydrogen ions are going into the cell too. So when you move sugar into the cell, you're moving hydrogen ions into the cell. So what's that going to do to the pH of the area outside the cell? Are you putting hydrogen outside of the cell or inside of the cell? Inside of the cell. And so those hydrogen ions are being taken away from the external environment. So is it going to make the outside more acidic or more basic? It's going to make it more basic. You're removing the hydrogen ions. leaving out their hydroxides. And more hydroxides means it's going to be more basic. So I'm thinking that the transport of sugar is going to make the pH level increase, right? Because we're removing the hydrogens. Are you following?
Yes.
All right. What would happen to the transport of sugar if hydrogen ions were removed from the external environment? If you remove the hydrogen ions, could you transport the sugar anymore? Nope. I'm saying I agree with you guys that if you take out all the hydrogen ions, these transport proteins are going to move the hydrogen and the sugar. But if you remove the hydrogen ions, I've never looked at this question before, so let's see. Do they give us an answer? Moment of truth. Uh-oh. Wait. It's frozen. Because hydrogen ion move into the cells with the sugar molecules, the transport of sugar into the cells would lower the concentration of hydrogen ions in the external environment, raising the pH. Did we get it right?
Yeah.
Yay! Removing hydrogen ions from the external environment would stop the entry of sugar into the cells by that mechanism. Did we get it? Yay! That's what we said. We don't have hydrogen ions to come with the sugar, then the whole mechanism shuts down. Now, had you ever heard of a transport protein like that? Had you ever learned about something like that? No. But did we take prior knowledge and apply it to a new situation? Yes. That's what honors is all about, you guys. Reasoning your way through things. And yes, that acids and bases are not in this unit, but we've learned about them before. You cannot forget. You have to remember. Why does this keep going? It goes on and on and on. Seems like it... Oh, it started all over again. Okay. Well, you guys, I'm going to end here. And you can go home and watch this again. Or those of you who weren't able to stay, hopefully you enjoyed. Please like and subscribe and get me some more. I want that old diamond subscribe button or whatever it is, huh? Right? If I get like 1 million followers, then I get paid, huh? They start putting ads on my thing. I'll never be as good as, Paul Anderson from Bozeman Science, but hey, I'm all that you've got in the flesh. So, signing off.
By the way,